Okay, welcome to our last and final lecture on thermodynamics. Homework 14 is due today. Hopefully you can put that in. And course evaluations need to be completed by tomorrow, so if you haven't done that, get on and do it. I do read the feedback, so it's important for you to go and fill those out. And our final is 1 week from today, so 10:15 to 12:15 here in this room. It's the end. Okay, so today we're reviewing the entire course, and I will skim through some of the earlier stuff that I feel like we probably know pretty well because we've done it so much, but if there's anything that you want me to go back and explain again, please don't hesitate to raise your hand and call attention to specific points. Okay, so first off, we'll talk about the laws of thermodynamics. And we didn't receive these necessarily in this order. We sort of went first, second, zero, and then third. But the zeroth law is the basis for temperature measurement. So if there are two systems that are in contact with a third system, and if, let's say, number 1 is in thermal equilibrium with number 2, and number 2 is in thermal equilibrium with number 3, then 1 and 3 are in thermal equilibrium one with another, even though they aren't touching. Okay, so this is how we can use mercury or alcohol within a thermometer to measure the temperature change. So if the mercury is in thermal equilibrium with the glass, and the glass is in thermal equilibrium with whatever substance it's in. The first law is conservation of energy. This is the basis for all of the energy analysis that we did throughout the semester. So we can change form from work to heat or heat to work using a heat engine, but we can never create energy and we can never destroy energy from this change. And then, of course, the law, theory of relativity, T equals mc squared, mass and energy can be interchanged, but it's a very large amount of mass that needs to be converted to energy. The second law dictates which direction natural processes will occur. So even though heat and work are equivalent in terms of they are both energy terms and we can add them together, the second law tells us that heat and work are very different types of entities, meaning that all of our energy in the form of work, like electricity, can be converted to heat. 100% of work can be converted to heat, but we can't go in the opposite direction and convert 100% of heat back to work. Usually it's around 60% in the best case scenario, and that would be for a totally reversible Carnot heat engine. So the second law tells us whether or not processes will occur naturally. So as we talked about perpetual motion devices, we looked at some examples of systems that looks good on paper. Like, hey, yeah, this, it doesn't violate the first law, energy is balanced, but from what we know about the natural process and laws, and particularly when we began our discussion of entropy, we learned that processes have to occur in the direction of increasing entropy in order to occur naturally. And then the third law was just that as the temperature approaches zero, then the entropy of the system will approach a minimum or zero in the case of absolute zero temperature and an absolute vacuum. So the energy balance in its various forms, the important thing to remember is that with a closed system, we don't have any flow work. And if we don't have any boundary work, then the internal energy change of the system is what's important to us. So Q in minus Q out plus work in minus work out is equal to M times U2 minus U1. Okay, for a closed system, our internal energy term is the governing energy change within the system. When we consider enthalpy, it's equal to the internal energy plus pressure times specific volume. So in cases where we have boundary work, this pressure times the change in volume gives some expansion term to our system. So for a fixed closed system where the boundaries are not moving, the only energy change within the system is due to just the change in the latent movement of the molecules and their energy levels. Once that system can expand or contract, then we have this additional PV term. Okay, so for a closed system, it's just equal to the internal energy. For an open system, now we have fluid that's moving in and out of our system, and then there's some work associated with movement of fluid through the system. So our energy balance is equal to the mass flow rate times the enthalpy on that side of the equation. Yes.
What if you have a situation, I remember one time we had an example problem where we were just supposed to put the boundary work to the other side and use H.
Mm-hmm.
But what if the boundary work was compression rather than expansion? Or that wouldn't even be a situation that we would have to solve?
Well, it would be a work-in term, so it wouldn't add, it would be a H minus.
But how would you just convert that directly?
You would just have to look up.
You would just have to know the.
Yeah, it only works when it's worked out and it's plus B. Okay, and in many cases, the kinetic and potential energy terms are negligible. However, if velocities are given and elevations are given in the problem, then you do need to consider them. You also need to be very careful about units, because it was 1,000 meters squared per second squared is equal to a kilojoule per kilogram. So if you do include velocities and elevations in calculating the energy terms, you have to be very, very careful about the units. And then we spent maybe one day, I guess, on unsteady flow, and the equation for that is here. It's very similar to open system steady flow, but in this case now, we have some energy change from the initial to the final state of our system. So with steady flow, the properties are not changing with time, but with unsteady flow, because they change with time, we need to consider a finite beginning and end point to when we analyze our system. So we may know the conditions initially, some flow happens, and then we know the conditions at the final state. So depending on which terms are given to us, whether we know the work and heat interactions, or whether we know the flow rates and what's coming in and out, or whether we know the initial and final state of the system, we may need to solve for one thing versus another. Okay. Hopefully you're very familiar with these equations. We use them all semester long. They should be almost like second nature to you. Just very important to know the difference between these types of systems and when each one of these equations would apply. Okay, so if you have a piston cylinder device with no inlet or outlet, what type of a system would that be? Closed. Okay, no mass flow across the boundary, so it's a closed system. If you had a turbine that's operating steadily, that would be open system steady flow. And if you had something like a pressure cooker where there's only an outlet, then it would be unsteady flow. And then the basic problem-solving techniques, I'm not going to go through those. We kind of have set out. Just remember, review those and go through them. The next several slides, and actually I think this lecture has more slides than your handout, just because I didn't want to print 20 pages. But a lot of the rest of this is going to be definitions for a while. So when we talk about a process, it's just the change that a system undergoes from one state to another. So starting at state 1, ending up at state 2, there's some process that gets you from state 1 to state 2. And depending on the type of process you select in order to have this change of state, this path will follow a different line. So the path is the series of individual points between state 1 and state 2 that it passes through between two equilibrium points. Okay, so this path can be whatever you want it to be. All you have to do is end up at state 2. For a quasi-equilibrium process, it's a solid line, meaning that we are fairly certain of every state that it passes through in between state 1 and state 2, or every position. If it's non-quasi-equilibrium, it's a dashed line, which means that we're approximating that it follows this path. We don't really deal well with that. It's more statistical thermodynamics. And then if this goes from state 1 to state 2 and somehow returns back to state 1, then it's called a cycle. So if you return back to the initial state, even if you pass through 7 or 8 states, in the meantime, once you get back to state 1, that's called a cycle. Closed system, we have no mass crossing the boundary. So mass cannot cross, but energy can. An isolated system is a special case where there's no mass flow and there's no energy interactions with the surrounding. So isolated systems are not always that interesting to study because not much happens. However, we do look at them when we're talking about entropy changes. And then for a closed system, the volume can change. So as we talked about with piston cylinder device, we have an additional work term that we have to consider. So if the volume is changing, if it's not a rigid cylinder, then we need to consider the effect of that in the boundary work term. And if the pressure is constant within the cylinder, it's very easy to calculate. It's just the pressure times the change in volume. If the pressure is not constant, you can, in many cases, plot it graphically and calculate it that way. So if there was a spring pressing on the cylinder or something like that, you can plot the endpoints. And if it's a linear relationship, it's easy to just calculate the boundary work graphically. An open system is also called a control volume, and an open system is any one which involves mass flow. So it can be an open system that's steady, like a nozzle or turbine or pump or compressor or any of those other steady flow devices we studied, or it could be unsteady. So in this case, we have a single inlet and there's mass accumulation within the device. So similarly, we can also have a moving boundary. And in most cases, if we have a moving boundary within an open system, it's going to be an unsteady flow open system because the properties will be changing with time. We talked about intensive versus extensive properties. So if you remember, intensive properties are independent of the size of the system. So if you were to create an imaginary line that divides this system in half, which properties would be changed and which would not? So temperature, pressure, specific volume, density, those aren't going to change with that imaginary line. But mass and volume certainly are properties that will change. And you can take an extensive property and turn it into an intensive property by dividing through by the mass. So volume is an extensive property. It depends on the extent of the system. But once you divide it through by the mass, you normalize it by the mass of the system, then it becomes an intensive property. So specific volume is intensive. Specific energy is intensive. The temperature scale, the most important thing to remember here is the conversions. So if you're converting from Celsius to Kelvin or Rankine to Fahrenheit, make sure in the problem, I think we had some problems with this on the last exam, that you're using the correct unit system. So if it's a problem where you're required to use English units, then you need to use absolute temperature in terms of Rankine, not in terms of Kelvin. So make sure of that. And then if you're calculating a temperature difference, then you don't need to include this plus 32 here. So the change in T in degrees Fahrenheit is equal to 1.8 times the change in temperature in Celsius. And then there's a similar conversion to go back. And just don't add on that 32 is the most important thing to remember. Pressure, we didn't do a lot with this, but it's important to remember the differences between absolute gauge and vacuum pressure. So the absolute pressure is the actual pressure relative to vacuum, like relative to zero pressure. So what is the pressure here within this room? The gauge pressure will be the difference between your actual pressure and what you're measuring within your device. So if I have a tire and it's pumped up above atmospheric pressure, and I put a gauge on it and measure the difference between the pressure inside the tire and atmospheric pressure. So this gauge pressure tells you the absolute pressure in the tire, which is higher than the atmospheric pressure locally. And then vacuum pressure is the same thing as gauge pressure, except it's when you're sub-atmospheric pressure. So if I pull a vacuum in like a canning jar or something, then the pressure is lower than my local atmospheric pressure, and so it would be considered a vacuum pressure. And that's just a way to denote it so that we don't measure a negative pressure. So vacuum pressure is just negative gauge pressure, but it's called positive vacuum. And then the variation of pressure with depth, just remembering that it adds in series. So if you have several different fluids that you're traveling through, you can add each one of those up based on the density of the fluid and the thickness or the height of this fluid column. So if you wanted to determine the pressure at some location below, you would take the pressure at the top, which in this case is atmospheric pressure, and then add on the density times gravity times the distance that you go down in the fluid. So these are fairly easy, and if you've had fluids, you've probably done it a lot. So the heat and work, they're similar in many ways in that they're both recognized at the boundary, and they're different in other ways too, as we find out in the second law, that heat and work are not interchangeable. Systems have energy, but they don't have heat and work. Heat and work are only recognized as it's transferred across the boundary or as work is done on the system or to the system. And then they're both associated with these processes. So at state one, I may be at some energy state, but I don't have a certain amount of work and I don't have a certain amount of heat. The only thing that is recognized is as I go from state one to state two, how much heat was transferred or how much work was done, Mr. Cool Guy Taylor. You're just trying to sleep under this glasses? So depending on the process that I use or the path that I follow, the amount of work done or the amount of heat transferred will be different. So they are very much dependent on how I go from state one to state two. Okay, so energy transfer by heat, it's recognized at the boundary, and all of these terms should be familiar. If you have a small lowercase q, it's just basically q divided by the mass, so it becomes an intensive property. The rate of heat transfer is the change in q over time, and then if the rate is constant, then we can multiply this q dot, which would be the heat flux, is called a heat transfer. Q dot times the time interval to get the total amount of energy that was transferred during that time period. And then this keyword adiabatic will show up a lot in problems, and it just means that there's no heat transfer. It's well insulated. We can transfer heat by conduction, which is physical contact between two surfaces, two solid surfaces. By convection, which is a fluid in contact with a solid, and by fluid, it can also mean a gas, like air. So fluid doesn't necessarily mean liquid. Forced convection is when that air is blown physically over that object, and natural convection is when the buoyant currents from just the heat rising cause the air to flow around this hot object. And then radiation is just by transfer of electromagnetic waves. So this is more just terminology and definitions. You don't ever actually have to calculate the heat transfer by these mechanisms. That's a different class. So work is energy transfer as well, and it's in basic terms, it's the mechanical energy is a force acting through a distance. So to be considered a mechanical force or mechanical work, there has to be a force acting on the boundary, or the boundary must move. And then again, on a unit mass basis, the lowercase just denotes the intensive property, which is work divided by mass. And then W dot is work per unit time, and it's also called power. So again, we ran into this problem on the last exam where I asked for the energy to be calculated, and some people were calculating the power, but energy is in units of kilojoules, and power is unit of kilojoules per second, or energy per time. Okay, so knowing the difference between power and energy is somewhat important as well. Types of work, we can have electrical work, mechanical work. This is just a force acting through a linear distance. We can have shaft work, which is a force through a rotational distance. And then spring work, which is a force with some linear spring constant associated with it. Potential energy is the work needed to raise a body, and then kinetic energy is the work needed to accelerate a body. So these are just different forms of work. Again, I'm going through these kind of fast because hopefully they all make sense to you. You're trying to correct me up over there. Okay, so let's look again at the energy balance. So in the most generic terms or simple terms, The change in energy of a system is just equal to the energy in minus the energy out. So energy in minus energy out can come in several different ways. You can have heat transfer in and out. You can have work in and out, or work done to or by the system. And you can have some energy transfer associated with mass coming in and out of the system. So if this is a closed system, then we lose this term here on the far right, and we just have work and heat associated with our system. So if we set this side of the equation, E in minus E out is equal to E2 minus E1. So we have Q in and out, work in and out, mass in and out is going to be equal to the internal energy change of the system plus this energy change due to the movement of the system, or the kinetic energy of the system, and the elevation change of the system. And then again in the rate form, E dot, you just put a dot over each of those terms. So M becomes M dot. We talked a lot about efficiencies, and there were different ways that we approached the subject for steady flow devices, for isotropic devices, for thermal transfer devices. But in essence, the efficiency of any device is our desired output divided by our required input. And if we have multiple devices acting in series, then we can say that the overall efficiency of those devices is just the product of the efficiencies. So if we have a turbine and a generator, for example, and the turbine has some efficiency associated with it, and the generator has some efficiency associated with it, if we want to know the combined efficiency, we can multiply those two efficiencies together. And the combined efficiency is always going to be less than either one of those two individual efficiencies, because they're both a number less than 1 multiplied one to another. It will serve to decrease the product. Pure substances, or just any substance that has a fixed chemical composition. This is more just a definition to remember and to know, because when we used our problems, or when we did our steady flow analysis and closed system analysis, we always assumed that what we were dealing with was a pure substance. So this is more just for definition purposes. The pure substances can exist in 3 different phases. The important things to remember about this is that the solid phase is the most organized, that the entropy will be the lowest, okay? Because this, if you look at the physical structure of the solid phase, it's very well organized, it's regimented. If you were to predict the location of the molecules, it would be much easier to do so in the solid phase than in the gaseous phase. So as the molecules start to move, they first go to the liquid, then to the gaseous phase. So the gaseous phase is very disorderly, but it's also high energy. So very disorderly means higher entropy, and orderly means lower entropy. The TV diagram, we use this mostly just in terms of looking at property values, just remembering that everything under the dome is going to be what? Saturated liquid vapor mixture. So if you want to determine where something is exactly under the dome, what's an additional term that you'll probably have to calculate? Quality. Okay, do we all remember how to calculate quality?
Yes.
Yes. Okay, so if you are still uncertain on how to figure out the quality when you're under the dome, work on that, because it will be required. The saturated liquid line delineates the liquid region from the saturated region, and then the saturated vapor line delineates the vapor region, or the superheated vapor region, from the saturated region. So just remembering what these diagrams look like and where, what these points represent, knowing that these lines may be lines of constant pressure on a TV diagram, but if you were looking at a PV diagram, they would be lines of constant temperature. Okay, so they look a little bit different. And this is the PV diagram, so lines of constant temperature go from down and to the right, but it looks similar in that there's this dome structure under which everything is in the saturated liquid vapor region. We know how to look up properties. We remember that V sub F denotes a saturated liquid, V sub G or any property value sub G denotes a saturated vapor. So those are the points that are right on the line of the dome. So the liquid line and the vapor line. And then the subscript FG denotes the difference between those 2 points. So if I wanted to determine the length of this line, what would be the length of that line? Okay, so what's my property here?
Difference between the saturated vapor, specific volume, and the saturated liquid.
Okay, so it would be Vg minus Vf. Okay, if I wanted to determine the distance between here in terms of enthalpy, then it would be Hg minus Hf, or HFG. So what does HFG represent in physical terms?
Isn't HFG the?
Well, this was a TH diagram. Right now, this is a TV diagram, but we could plot it in terms of H. It would look very similar. But physically, what is it? What does HFG represent?
The enthalpy that's in the saturated vapor mixture.
Okay. So if I were to vaporize something and go from saturated liquid to a saturated vapor, HFG is the energy required to change forms. So in order to go from a liquid to a vapor, that's the amount of energy that must be added to the fluid in order to make that phase change happen. So that's what physically HFG represents. And in our last homework, we had something called HIF, which was the latent heat of solidification. It's not called that, something else. Fusion, latent heat of fusion, which is the energy required to go from a liquid to a solid. So physically understanding what it means in terms of enthalpy, that's the amount of energy that's required both to increase the internal energy of the substance to the point where it's moving, and then it takes into account the expansion of the substance as it changes form. So it's a constant pressure process. We increase the internal energy and we increase the specific volume. So the enthalpy takes into account both those two terms as we vaporize a substance. Okay, quality. This is again a refresher on how to calculate the quality. So what it represents physically is the mass of vapor divided by the total mass of the substance. So it's giving us an indicator of how far along this line we actually are. And then the average property values, again, are calculated in this way, where y this represents any property value, so enthalpy or entropy or specific volume. The ideal gas equation, we've seen it in several different forms. PV is equal to RT is the most general form, where this R is specific to whatever substance we're using. So for nitrogen or for air or carbon dioxide, those are all tabulated in the back of the book. And it's equal to the universal gas constant divided by the molar mass of whichever substance we are studying. We've also seen it in this form where PV, capital V, is equal to MRT, just an alternate form. And if we're dealing with a closed system where the mass is fixed, then we can say that M is equal to PV over RT. And if M1 equals M2, then we have P1V1 over RT1 is equal to P2V2 over RT2. And if it's the same gas, then R is also equal. So we can set them equal to one another in this way. So that allows us to find perhaps the second temperature. If we know the initial temperature, pressure, and volume, and the final pressure and volume, we may be able to find the second temperature. Just depends on how the problem is set up, but in some cases they may be useful to you. Very important to remember that this only applies to ideal gases. Okay, you cannot use this for water or for R134A. Only applies to ideal gases. It also only applies to ideal gases where the mass is constant. So if you have an open system, let's say a compressor with carbon dioxide in it, you can't use this because the volume changes, the mass changes, it's not necessarily fixed. Okay, and then some other equations of state, these will not be on the final. You don't have to worry about that. So there were some others in case you want to save these notes for posterity. Okay, and we talked about how there are certain gases that are always ideal gases. So they behave like an ideal gas all the time at normal operating conditions. So like air, carbon dioxide, nitrogen, things like that. But then we talked about certain conditions where other substances might be considered an ideal gas, and how do we correct further deviation from ideal gas behavior. So we said that at very low pressures, that gases will behave like ideal gases regardless of what temperature they are. And then at very high temperatures, they'll also behave like ideal gases, except when we have also a very high pressure, okay? And then the deviation from ideal gas behavior is the greatest when we're operating right at the critical point. And if you remember back to that video, it's because the state of the substance is very nefarious. It goes directly from a solid to a vapor without really evaporating. It just poof, sort of happens. But if we can correct for the deviation from ideal gas behavior. So let's say that we're operating somewhere in this region where we're not totally at a high temperature, we're not really at a low pressure, so we try to find something here. We can calculate this correction factor Z, which allows us to, I guess, correct, the correction factor. It allows us to get a little bit closer to the actual value in our calculations. That's called the principle of corresponding states, because although different gases behave differently at different temperatures and pressures, if we normalize each of those gases by their critical point, they all behave very similarly. So the reduced pressure is the pressure divided by the critical point pressure, and the reduced temperature is the temperature divided by the critical point pressure. And we can do something similar for specific volume. So these critical point pressures and temperatures are dependent on which gas we're dealing with. Okay, so these values are tabulated also. I think table A1 is where they are. That if we have a given pressure, then we can divide through by the critical point pressure. Then we can use this compressibility chart to find our Z factor. So let's say we calculate our P sub R and we calculate a T sub R. So we find P sub R here. Let's say it was 0.7. And then we follow that line up until we encounter T sub R. And we'll just say we calculated it as 1.0. So right here where those two lines intersect, we go over to this side of the chart and read a Z value of 0.7. So again, if our reduced pressure is 0.7 and our reduced temperature is 1.0, then we just find where they intersect to read the Z value off the chart. So we did some of these for homework. There was one on the exam. Hopefully it's familiar to you. Just remind yourself how to do it. And if not for this class, then it may be on the FE exam later in your life, unless you've already taken the FE exam. Did you have any one of those?
I didn't take the FE.
Oh, you didn't take it?
I'm taking
How
it
can you
next
take
semester.
the right review session?
Because I'm taking it next semester. I just want to get the reviews in, so I just come to them, but I'm not taking it until next semester.
Okay. And then we have something called a polytropic process, which is the relationship between pressure and volume is some known relationship. It's not necessarily linear, but the way that they change one to another may be some constant value. So ideal gases are a good example of gases that follow a polytropic process. So if we know this relationship, so we have PV to the N, and N can be any value. It can be a positive value, it can be a negative value. Then we can calculate the boundary work due to that polytropic process using these equations. So if N is not equal to 1, then this is the equation for boundary work. For the special case where N is equal to 1, then this is how we calculate the boundary work. And then for an ideal gas, this is the equation here, where P2V2 is equal to T2, P1V1 is equal to T1. So those are just FYI, and they'll be on, yes.
Student question, what's polytropic mean? There's probably what it's called.
What does the word itself mean?
Like, yeah, if it's a polytropic process, what is the process is?
It means that it's a process where the pressure and the volume, they don't vary linearly, but they have some known relationship. So the reason that we care is because if we remember back to the equation for boundary work, is equal to the integral of P dV. So it behooves us to know some functional relationship between P and V. And then there are certain types of processes that have some functional relationship where P, V to the N is equal to some constant value. So regardless of the initial pressure or volume that you start with, you know that as you start changing the pressure, the volume changes in a predictable way and there's some constant associated with that. So PV equals RT. That's a special case where PV equals RT is an ideal gas. So PV varies according to this constant RT. So for an isothermal ideal gas process, then C is equal to RT. But poly means many, and tropic, I don't know. I haven't broken that word down to figure out why it's polytropic, but yeah. It just allows us to analyze certain types of systems in order to determine the boundary work when the pressure is not constant. So if the pressure is constant, we just take pressure out and it's just P delta V. But we have many types of systems where that's not the case. And this is an example of a type of system where this isn't the case, but there is another easy trick that we can use to know the functional relationship between pressure and volume. So that's why. And then boundary work, of course, is just the force times the distance. So this was just, I don't know why this slide is later, it should have been before, but boundary work is equal to the integral of PdV, just based on moving this fictional piston some differential amount, and then the cross-sectional area there multiplied by that amount gives us a dV. And it's important to remember that the area under the curve on a PV diagram represents the work done, the net work done, not just necessarily the boundary work, but it's all the work done during that process. There may be electrical work and spring work and other things, shaft work in there. But if we know this path, and we can, if we know the functional relationship, then we can calculate the integral. But if we don't know the functional relationship, but we know maybe that it's a linear connection between point 1 and 2, that's when we can just plot it on paper and graphically calculate the area under that curve to figure out the total boundary work, or the total work done under the curve. Enthalpy and internal energy, we talked about this. So for a closed system that has boundary work involved and it's a constant pressure process, then we can move this boundary work to the other side of the equation and we have our change in enthalpy. So this phase change along the saturation line would be an example of when the pressure is constant and allows us to just combine the change in energy term with this boundary work term to get enthalpy. Specific heat, we had two different constants. They're not constants, but two different terms. So the specific heat at constant volume is the amount of energy required to raise the temperature by 1 degree as the volume is maintained constant. And if you notice here with constant volume, then it represents the change in internal energy. So if you think about a closed system, constant volume, when we calculate the change in energy of that system, it's equal to the change in the internal energy. Okay. But if instead of holding the volume constant, we now hold the pressure constant, we have this enthalpy term that comes in because now we're allowing that substance to expand. So we have the internal energy term plus the flow energy term. Okay. But regardless of your process, you can still use C sub V and C sub P for any process. So if you wanted to calculate the change in enthalpy for constant volume process, you can use C sub V to calculate delta H. Do you have questions about this? I feel like I don't want to say too much, but I don't want to not cover things that you guys don't understand. I feel like we talked about
There's a difference in numbers of CB and CP, and it still baffles me a little bit, and I can use one or the other.
I think when you say you can use one or the other, you have to use a respective for like, the CP for the H or the.
Right, if you're calculating a change in enthalpy, you have to use C sub P. If you're calculating a change in internal energy, you have to use C sub P. But you can calculate the change in internal energy at a constant pressure, during a constant pressure process. So the change in internal energy is going to be the same regardless of if it's from state 1 to state 2, because internal energy is based on the initial and the final temperature, and the same thing for the enthalpy. But what you're calculating when you calculate the internal energy is just that internal energy change. And when you're calculating with the enthalpy is you're calculating the internal energy plus this flow work and or expansion term. So the way that they're defined just allows them to be related to real property values, but they can be applied to any type of system.
Just not tied to ideal gases or anything like this.
Right. Oh my goodness. If you want to determine the change in energy for an ideal gas, you can use tabulated data. So we have a couple of tables in the back. Air is the most comprehensive, but there's also some that are in terms of per molar mass. So the tables are going to be the most accurate. You can also use C sub V and C sub P, and if you know some functional relationship for C sub V and C sub P, then you can integrate. So you can perform this integral. If you knew how C sub V varied with temperature, then you could integrate and calculate delta U. Probably you're not going to ask to do that. And then the third way would be using an average C sub P, where you can calculate the average either at the average temperature, or you can find C sub P at the initial, C sub P at the final, and then average those two together. So either way. And it's reasonably accurate. Over small intervals, it starts to become less accurate as you're going over large temperature differences. Okay, steady state devices. So again, here's our open system energy equation. It's in a slightly different form. It's all the ins are on this side and all the outs are on this side. You can also look at it in this way. Q net in minus work net out is equal to that. So if it's a steady state system, then the mass is constant. So we have the MDT is 0. Energy is constant. The EDT is 0. And there's no boundary work for a steady state system because our volume is constant. So it simplifies our equations down. Some examples of steady state devices: turbines, compressors, pumps, pipes, heat exchangers, anything else I forgot, throttling valves. So Q dot is the rate of heat transfer between the control volume and the surroundings. So if Q dot is, Q dot is out, it's a minus Q out. Q dot in is a positive value. W dot is power. There's no boundary work, so we just have to look at like electrical and shaft work within our steady flow system. The change in enthalpy accounts for the internal energy change as well as the flow energy or the amount of energy that's required to push the fluid through the system. And in many cases, we can approximate it using C sub P delta T. Kinetic energy changes, again, watch your units. If velocities are not given, you can assume that you can neglect it. If velocities are given, then you have to calculate it. And the same thing goes for elevation changes as well. If they're given to you, calculate it. If they're not given, assume that it's negligible. Always, always, always keeping track of units. We can perform mass balance. So in general terms, Mn minus M out is equal to the change in the mass of the control volume. For steady flow, M in is equal to M out, meaning that the mass control volume does not change. So M in equals M out. For steady flow single stream, just have M dot 1 is equal to M dot 2, where this is in and out, which is also equal to the density times the velocity times the area, cross-sectional area of the flow. If it's steady incompressible flow, meaning that the fluid density does not change, then this V dot term is equal to, V dot in is equal to V dot out, so that the densities are the same, or in other words, the velocity times the cross-sectional area of the inlet is equal to the velocity of the cross-sectional area of the outlet. Okay, so this is all just things. Okay, nozzles and diffusers. Nozzles serve to increase the velocity. Diffusers serve to decrease the velocity. Nozzles will decrease the pressure, and diffusers will increase the pressure. Usually there's no work, heat, or potential energy interactions, but we do have to consider kinetic energy changes. Turbines and compressors. A turbine is a work-producing device, and a compressor is a work-consuming device. If any information is given to you about heat transfer, then you would have to assume that there's something happening. If it's not given or there's no way to calculate it, you can assume that they're adiabatic. Usually potential energy changes are zero, and usually kinetic energy changes are zero or negligible. So certainly for compressors and then sometimes for turbines. However, work is not zero. Throttling valves is important because it's an isenthalpic process. So there's no work, no heat, no potential energy, no kinetic energy changes, but we do have this H1 is equal to H2. So this allows us to determine initial and final pressures or initial and final specific volumes, for example. So just knowing that enthalpy is constant across that. And for an ideal gas, enthalpy is a function of temperature only. So it means that the temperature will also be constant for an isenthalpic process. Mixing chambers, you have multiple fluids coming in, mixing together, and then going out at a single outlet. Usually there's no work unless there's a stirring mechanism involved. Usually the heat transfer is negligible, kinetic and potential energies are negligible. So m dot in is equal to m dot out. If you have multiple inlets, in this case there's 2 inlets and 1 outlet, then you have to be sure to balance your mass flow rates in that way. And then the energy equation is just this. Heat exchangers, similar to mixing chambers, except the fluids are kept distinct from one another. So they have multiple inlets and outlets, but heat is being transferred from one fluid to another. So it'll transfer from the hot fluid to the cold fluid. Usually there's no work interactions or potential kinetic energy interactions. And then Q dot is 0 if you take the entire heat exchanger as the system. So if there are no losses from this heat exchanger, you're looking at the whole thing as your system, it's 0. But it is not 0 if you look at each of the individual fluids as a system in turn. So there's 3 separate energy balance equations that you might do for a heat exchanger to allow you to solve for your unknowns. Pipes and ducts, a lot of different stuff can happen. You just have to look at them and know what's going on. Not very interesting. With unsteady flow, our control volume properties do change with time. However, it's over a finite time period, so we know the beginning and the end conditions. And the control volume can change in size, it can change in shape, and properties can change. So there's a lot of things that can change in unsteady flow. The general form of the energy equation now, we can't neglect this side of the equation, the change in energy of the system over time, or just the change in energy of the system. So we have to consider that. And then when kinetic and potential energies are negligible, it reduces down to this form. Again, you can put a positive sign here and flip these two. I haven't changed that everywhere in my notes, but I've changed it most places. So it's equal to this, and hopefully you remember these equations. I don't need to go through term by term because we want to spend more time talking about entropy. Heat engines convert heat to work. Important things to remember, they can convert only part of the heat to work. They can't convert 100%. They have to convert part of it to work and then reject the rest to a heat sink operating on a cycle. A steam power plant is a good example of a heat engine. So we have Q in to the boiler, some work output from the turbine, and then some heat rejected through the condenser. And many times a little bit of this work output will be used to drive the pump. The thermal efficiency of this plant is the work output or the desired output over the required input. So net work out divided by the total heat in, the thermal efficiency. And again, it's always going to be less than 100% because you cannot convert 100% of heat to work. Usually it's less than 60%. Kelvin Planck statement and the Clausius statements are equivalent statements of the second law. It is impossible for any device to receive heat from a single source and produce work. So in other words, no heat engine can convert 100% of heat to work. And then the Clausius statement is that it's impossible to transfer heat from low temperature to high temperature without putting work into the system. Refrigerators are heat engines operating in reverse, sort of. So we have a network input now. We're trying to transfer heat from a cold space to a hot space. So if it's a refrigerator, our desired output is that we're making this cold space colder. So this is our equations for coefficient performance. The heat pump, our desired output is to make the hot space hotter. Those are the equations for that. Again, they both require a work input. They're both analyzed in much the same way. The main difference is knowing whether your requirement is to make something colder or to make something warmer. So an air conditioning system is actually a refrigerator, not a heat pump. So it's analyzed as a refrigerator instead of a heat pump. We're trying to remove heat from the indoors and deposit it into the warmer output. Reversible processes can be returned to the original state. Some definitions: internally reversible means that the system can be returned. Externally, the surroundings can be returned. And then totally reversible, they can both be returned. So in real life, we have systems that are internally reversible or externally reversible, but we do not have systems that are totally reversible. And then just some examples of irreversibilities: so friction, expansion, resistance heaters, and many of those things. So we've kind of talked about those a lot. Perpetual motion machines, in order for a system to occur, or a process to occur, it needs to satisfy the first and the second law. So if it violates conservation of energy, it's a perpetual motion machine of the first kind, and if it violates the second law, meaning the direction of energy transfer, then it's human to. Okay, the Carnot cycle was a reversible cycle that we said was the best case scenario for any reversible heat engine, any reversible refrigerator, and any reversible heat pump. So the Carnot cycle operates on these 4 cycles. I don't need to go through those necessarily. But the 2 Carnot principles are that the efficiency of an irreversible heat engine is always going to be less than that of a reversible heat engine between the same reservoirs. And then all reversible heat engines operating between the same 2 reservoirs will have the same thermal efficiency. A Carnot heat engine, we can calculate the efficiency now. Before, we determined that it was 1 minus QL over QH. If it's a reversible heat engine, we said that the temperature ratio is equivalent to this Q ratio. So the ratio of the heat transfer is the same as the ratio of the temperatures of those reservoirs. And the Carnot heat engine represents the best case scenario, the highest efficiency for any system operating between those 2 reservoirs. And it's important to note that these temperatures are given in terms of absolute temperature units, so either Kelvin or Rankine. Carnot refrigerator, again, it's the best possible refrigerator, and the COP can now be determined in terms of temperature, not just the Qs. Same for the heat pump, best possible heat pump. And now we get to entropy. Okay, so the final will, it will be comprehensive, but it will focus more on chapter 7 than anything else. So for entropy, we've determined that there's a couple of properties that are different between entropy and energy. So for energy, we cannot create it, we cannot destroy it. Entropy, we can create. Okay, so for a reversible process, the change in entropy is equal to the integral of del Q over T. But for an irreversible process, we have this additional term called the entropy generation. So in order for a process to really occur, this entropy generation has to be either zero, if it's a reversible process, and in real life it can come pretty close to a reversible process, or greater than zero for an irreversible process. If this entropy generation term turns out to be less than zero, it's an impossible process. It can't really occur. Now, we've done some examples in class where we've had the entropy of our system change, and sometimes that change was negative. So how does that fit into this discussion here?
Evaluating the entire system.
Okay, so we're just looking at the system. We're not looking at the system plus the surroundings. So the entropy of a system can decrease. But if we look at the system plus the surroundings, the entropy must always increase. And then if it's an isolated system, the entropy generation is the system plus the surroundings. And this is always greater than or equal to zero. The increase of entropy principle, as we just discussed, that the entropy generation is a property of the process. So the system can have some entropy change just because entropy is a property value. So the entropy may decrease if we remove heat from the system. However, this process still generates entropy because we're adding heat to the surroundings, and that's an entropy generation process. So the entropy generation is a property of the process itself. So we can do things in a more reversible way in order to decrease the amount of entropy that we generate. At any time we have irreversibilities in our system or irreversibilities in our process, we generate more entropy. So friction generates entropy, head loss generates entropy, heat transfer generates entropy. So any of those losses that we normally associate with a reduction in efficiency are ones that contribute to entropy. And it's always positive, or in the case of a reversible system, it will be zero. An isolated system, we said, could be a system plus its surroundings, and we consider the universe to be an isolated system, and the entropy of the universe is constantly increasing. And then again, this is sort of just a restatement of what we've been saying for the last several slides. The entropy change of a pure substance is calculated or looked up the same way that any other property value is determined. So entropy is a tabulated value. It has the same entropy at fluid state, entropy at the gaseous state, and then the difference between those two. So if we want to determine, this should have an X here.
In our slide, it has.
That's good to know. Okay, so the entropy of a saturated mixture is going to be the entropy at the fluid state plus the quality times the difference between the fluid and the gaseous state. Okay, so again, entropy is a property value. Just like all our other property values, it can be looked up from the tables, and we treat it the same way. An isentropic process is one where the entropy does not change from state 1 to state 2. So we can have an isentropic process that has no entropy change, that will have entropy generation though. So if our turbine, for example, is adiabatic and reversible, so if those two keywords come in, it's adiabatic, there's no heat transfer, reversible, there's no friction or other losses, then we know that the entropy doesn't change. Okay, so that allows us to fix the state when we would otherwise not know the outlet conditions of the turbine. So you always need to look for those two keywords, adiabatic and reversible equals isentropic, because it won't always say necessarily isentropic. Some other examples might be if it says that it's an adiabatic process, find the best case scenario for the work output. Okay, well, the best case scenario would be when it's a reversible turbine. So if it's already, you know, it's adiabatic and you can assume it's reversible, then it would be isentropic. The Mollier diagram, we looked at this. It was a way of visually representing the losses in our system or the irreversibilities in terms of how much this entropy changes for a given work production or work consumption process. So if we see that we're going straight up and down on an HS diagram, that means that we're getting a maximal work output and no entropy change in that process. So ideally, we want our process to have this straight up and down on an HS diagram. Any deviation in delta S means that we have some irreversibility associated with the process. We came up with a couple of equations called the Gibbs equations, and this is just how they are derived because H is equal to U plus PV, and then TDS is equal to du plus PdV. We can just rewrite these equations. So we have the first and the second Gibbs equation, which allow us to relate entropy to other property values. So if we know how the enthalpy changes and the pressure changes within our system, then we can calculate how the entropy changes as well. So depending on what information you know about your system, you may want to use one of these versus the other. So if pressure is constant, then you'd probably want to use the first Gibbs equation, whereas if the specific volume is constant, then you use this one. We can make some simplifications. So using these equations, plugging them into the functional relationship for entropy, we can come up with the entropy change for an ideal gas. So it's important to remember that this can only be used if you have an ideal gas with constant specific heat. So this is the approximate analysis, meaning that you're making some assumptions that allow you to use this equation. The foremost being that it's constant specific heat. So there's two different versions of this same equation. One has a change in specific volume or the ratio of specific volume change. The other has the ratio of the pressure changes. There's also additional relationships that we can derive that allow us to relate property values for an isentropic process. So this is just the entropy change, and when delta S is equal to 0, then we can rearrange those equations to come up with these relationships. So it allows us to calculate the change of pressure, for example, if a temperature difference is known for an isentropic process for an ideal gas with constant specific heat. Okay, so all of those assumptions have to be valid in order to use these equations. If we want to do the exact analysis, now we need to use the table. So in the table, there's something tabulated called S superscript 0, and it's a reference entropy. So this reference entropy is equal to the integral of C sub P of T dt over T. So these are already tabulated for us. We don't need to calculate this integral, but it allows us to calculate the entropy change using the tables rather than assuming constant specific heat. So this takes into account how the specific heat varies with temperature. So this function, S superscript 0, is a function of temperature only. Just like enthalpy and internal energy for an ideal gas are functions of temperature only. But entropy for an ideal gas is a function of temperature and pressure. So this allows us to look in the tables, which are in terms of temperature, to determine this reference entropy. Then we can plug it into this equation, which calculates the actual change in entropy, taking into account the change in pressure. So if the pressure is constant, then this P2 over P1 goes to 1, and the natural log of 1 is 0, and this term drops off. So if it's constant pressure process, then your reference entropy is equal to your actual entropy because it's a function of temperature only. You don't have to worry about the pressure. But this is a correction factor that allows us to tabulate these values based on temperature and use them to calculate the actual values, which are based on temperature and pressure. So instead of having a whole new table to do it with temperature and pressure varying and having to interpolate, you can just use this to calculate it. Does that make sense? Do you guys remember doing this? Okay, so that's just the important thing to remember, that if you're told to use the most accurate method available, that would be the exact analysis, not the approximate analysis. And then similarly, if our process is isentropic, then this S2 minus S1 goes to 0, and we can solve for the second state of an isentropic process using this method. So let's say we knew the pressure change, we could plug it in here, and we knew the initial temperature, we could look up S1, plug in the pressure change, and then find S2, go back to our table and see which temperature corresponds to that S2 reference entropy. Okay, so this is ways to calculate the second state when your process is isentropic and specific heat does vary. So it's the exact analysis. Relative pressure is also another way to do it. So we have an additional column in our ideal gas tables that give us relative pressure. So if we know the pressure ratio, we know it's for an isentropic process, it's equal to the ratio of these relative pressures. So it's also another way that we can look up, if we know the initial and final pressure, we can look up these reference pressures to determine the final temperature, right? Same thing can be done with the volume ratio as well. And it's important to note that although this ratio P2 over P1 is equal to this ratio, P2 does not equal PR2 and P1 does not equal PR1. It's just the ratio of those two pressures is equivalent. The energy balance for steady flow devices is this basic form of the equation here. If it's an internally reversible process, then we have just these partial derivatives on it. But because we have the Gibbs equations, we can put in this TDS is equal to DH minus DDT. So if we rearrange and solve for DH and plug it in, then we end up with this term here. So del Q, we plug that in, this simplifies. So our reversible work for a steady flow device is equal to this VDP. And in general, we neglect the kinetic and potential energies. So this was how we determined the reversible work for a pump or a compressor. And if you remember, we talked about how this work input is going to be lowest when this specific volume is lower. So a pump, in order to create the exact same pressure difference between pumping a liquid or compressing a gas, it will require much less work to pump a liquid than it will to compress a gas. That's one of the main reasons why steam power plants have a pump rather than a compressor in order to get back up to boiler pressure. So it requires less work input. We also determined that for a compressor, because the specific volume is so much larger, we want to do what we can to reduce it during the compression process. So we can have some, in the isentropic process, we don't apply any active cooling, but this is the equation to determine how much work it takes to compress the gas. For a polytropic process, we can apply some cooling to the system as it's being cooled, and it reduces the amount of work we have to put into the system. And for an isothermal process, we are applying the maximum amount of cooling so that our temperature doesn't increase at all, so our specific volume doesn't increase at all. And this is the work required by the compressor. We can also, because it's somewhat difficult to cool a compressor as it's compressing, we can compress first to some initial stage, cool the gas, and then compress again to the second stage. So that's multi-stage compression with intercooling. And we determined that the work will be minimized when this equation holds true. So if we take the derivative of this equation and set it equal to 0, we find that the square root of P1 times P2 is equal to this intermediate pressure. So if we want to solve for Px at the best case scenario, it's just the square root of P1, P2, then we can just plug it into this equation and solve for the work required if we're going to cool the gas in between two separate stages of compression. So instead of compressing all the way from the initial to the final pressure, we stop somewhere in between, cool the gas, and continue on. So this allows us to have a little better work performance and require less work input. We also developed some efficiencies based on the isentropic case versus the actual case. So isentropic efficiency for a compressor is the isentropic compressor work divided by the actual compressor work. So this would be like our desired output, but this is our actual output. And if we neglect any kinetic and potential energies, then this is the equation that we would use, where H2S is determining the enthalpy if our process was isentropic. So first we determined if, the initial state. So at H1, maybe we're given the temperature and the pressure, and we can look up the initial enthalpy. Then we say, okay, what would happen if my enthalpy or my entropy was constant, and I solve for the enthalpy at that case. So that would be the isentropic case. The actual case is, okay, so let's say our isentropic efficiency is 85%. Now I can solve for my actual enthalpy at the exit. And although the isentropic case is the best case scenario when we don't apply any cooling methods to a compressor, we can actually improve the performance further by applying cooling, which serves to reduce the entropy. So if we cool it enough so that the temperature remains constant throughout the compression process, then we have something also called the isothermal compression efficiency. So the isothermal compression efficiency is the isothermal compressor work divided by the actual compressor work. Okay, so all of these equations and stuff will be given to you in your equation sheet, but just understanding when they apply and how to use them. A similar idea for a turbine. The actual turbine work is going to be less than that of the isentropic turbine work. But if we assume that it's the isentropic case, solve for this isentropic enthalpy, then if we know the efficiency, we can calculate this H2A to determine the actual output of the turbine. Same for pumps, but in this case, with the pump, we know that the steady flow pump work is equal to B times P2 minus P1. And nozzles have to do with the kinetic energy of the nozzle. So it's the actual kinetic energy at the exit divided by the isentropic kinetic energy at the exit. So we can just use these equations in a similar manner. If we assume that it's isentropic, then we can calculate the isentropic enthalpy. Then if we know the nozzle efficiency, we can calculate the actual enthalpy, and then we may use the actual enthalpy to solve maybe for the actual outlet velocity. Okay, so entropy balance, this was the last section that we covered on entropy. And basically we have a couple of different ways that entropy can be transferred in and out of the system. It can be transferred by mass flow and by heat. So for a closed system, we only have entropy transfer by heat. And then for an adiabatic closed system, the entropy generation is just equal to the change in entropy of the system. For system plus its surroundings, you just find the individual change in entropy of the system plus the entropy change of the surroundings. For an open system, now we have entropy transfer due to heat and mass flow, so you have to consider all of these terms. For steady flow, then we set the SPT equal to 0. If it's single stream, then we just have a single m dot, and if it's adiabatic also, then it further simplifies to this. We talked about the Rankine cycle, where we had the Carnot cycle was not suitable to us to use in a steam power plant, so we modified it slightly. These are the states and the processes of the Rankine cycle and the energy analysis of the Rankine cycle, so important to review that, and particularly to remember when you're finding the work of a pump to use V times P2 minus P1. And of course it deviates from actual Rankine cycle because the turbine and the pump are both actually irreversible. But there are certain things we can do to increase the efficiency, and so this talks about that. The last lecture that we had, we talked about IC engines and the air standard cycle. So in gas power cycles, we have a gas throughout the process. So in a steam power plant, we can alternately vaporize and condense. Then in a gas power plant, we don't have that option, but we can make certain assumptions that allow the analysis to be a little bit easier. So we assume that the working fluid is air, which loops continuously. All the processes are internally reversible, and then we replace combustion with heat addition and replace exhaust with heat rejection. So that was deemed the air standard cycle. And this is mostly like definitions and terms from this section. So you need to know all of these definitions and terminology. And then the difference between the Otto cycle, the diesel cycle, and the Brayton cycle. So those are there for you to review. So the final exam, 2 sheets of paper with your own notes. And I'm going to hand out, this is the equation sheet that will be used on the final exam.
This says here 3 sheets of paper.
It really does agree.
It's supposed to say two.
So 2 sheets front.
2 sheets front and back. Okay, you're ready to put that one. But this is the exam equation sheet. So as before, I will provide this equation sheet to you with tables. So if you want to use this as one of your note sheets and annotate it and make sure you understand it, that's fine, but that counts as one of your note sheets. So you can just have it for review, so you can become familiar with where these equations are, make sure that you know what those equations represent and how to use them. This exam will be slightly longer than what we've done in class, but not significantly longer. We have 2 hours instead of 70 minutes, so it's about 30% longer, I would say. And it is comprehensive, so any of the definitions that we've given in the past are fair game for use on this exam. Hopefully, those are just part of your vocabulary now, so that they won't be stumbling blocks for you, that you'll understand them because we've used them so many times in class. So don't worry and freak out. It's the same as the exams we've had in class. It won't really be any more difficult. It will just be slightly longer. So just remember and prepare and practice. And if you have questions, then I'll be happy to answer them. See you next Thursday.